In today's lesson, we are going to look at section 2.4, continuity of a function. We're going to determine if a function is continuous or what type of discontinuity exists, determine continuity graphically and algebraically. When do limits fail to exist? There are 3 times when limits fail to exist. The first one is when the left and right-sided limits are unequal. This notation would look something like this. The limit as x approaches c from the left of f of x does not equal the limit as x approaches c from the right of f of x. The second time a limit will fail to exist is when the function increases or decreases without bound as x approaches c. The limit becomes infinite, or asymptotic is another term to be used. The third reason is a limit might fail to exist due to oscillation as x approaches c. When do limits exist? A limit exists when the left and right-sided limits are equal to the same number. And the key thing there is a number that exists in the real domain. A function is continuous if, the informal definition is a function is continuous if you do not have to pick up your pencil while drawing it. Its graph has no breaks in it. A function can be continuous at a point, such as continuous at x equals 1. Or on an interval, continuous on the whole interval from 1 to 3, or over the entire domain of a function as well. Here is an example of a continuous function. It is in fact, it is continuous at x equals 1, right here. It is also continuous on the interval from 1 to 3, and it is continuous over its entire domain from 0 to 3. And this is just one example of many examples of functions that can be continuous. Types of discontinuity. So this is one of our key focuses for today's lesson, and one of the objectives is identifying if a function is discontinuous, what type of discontinuity does it have? So one type of discontinuity is called infinite discontinuity at x equals c. We already looked at this with the graphical representation, and in fact, here's a graph to kind of show you. It's where x grows either increases or decreases indefinitely as x approaches the value c from the left or from right. Typically, it's an asymptote that we've seen with rational functions in our past. The second type of discontinuity is called jump discontinuity, and that's when a function has jump discontinuity at x equals c if the limit of the function as x approaches c from the left and right exists but have 2 distinct values. So this is one we've seen graphically already, and it has a name for it for discontinuity. It's called jump discontinuity. Sometimes you'll refer to it as step discontinuity as well. The third type of discontinuity is called removable discontinuity, sometimes also referred to as a hole or point discontinuity. Sometimes the language that you use for these can kind of blend between things, but this one is usually called a removable discontinuity if the function is continuous everywhere except for the value of the hole at x equals c, and we have our example here. So these are the 3 types of discontinuity, which will cause a function to be discontinuous at a certain point. All right, here is an example of a continuous function. What we're going to do in this slide is have a couple different pictures pop up graphically to analyze the type of discontinuity we have. So for this first graph, there's a hole in the graph. So we would say that this graph has point discontinuity or removable discontinuity. How about for this one? Looks similar, except for it has a closed circle at the hole as well. So this is a piecewise function, but it still has point discontinuity. It is not a continuously smooth curve for it. There is a removable discontinuity at a point. This graph has step or jump discontinuity and is also non-removable. This graph has infinite discontinuity, where it's growing without bound as it approaches x equals c. And this is called a cusp in a function. It is still a pattern. If you think of the informal definition of continuity, you don't have to pick up your pencil and it's a smooth curve that you're drawing from left to right. So this is a continuous function. The word cusp we'll look at a little bit closer, but it tends to have an abrupt change in the curve as you have that. Note, a function can be discontinuous at some x value, but be continuous at all other values or other values in the domain. Continuity on an open interval. A function is continuous on an open interval, a comma b, if it is continuous at each point in the interval. A function that is continuous on the entire real line from negative infinity to infinity is everywhere continuous. Formal definition of continuity in terms of limits. This is very important for today. This is probably the #1 piece of today's lesson, so please write this down. Write it down several times, commit it to memory. It is a big key element of continuity, the formal definition, the calculus definition using limits. There are 3 requirements. I often say write them down like a checklist and make sure that it meets all those parameters of the checklist. First one, f of c must exist. Second one, the limit as x approaches c of f of x must exist. And the third one is f of c must equal the limit as x approaches c of f of x. So all 3 of these parameters must exist. The function must exist at c, the limit must exist at c as x approaches c of f of x, and they must be equal to each other. There is one other thing that's understood, is this implies that for the limit property that the limit from the left side and right side of f of x are equal at c. So again, I encourage that you pause and write down these 3 properties because they are very vital for as we move forward into examples more with algebraic. All right, here's some examples of some graphical ones. In the following graphs, determine if the function f of x is continuous at the marked value of c. And if not, determine which of the 3 rules of continuity the limit or the function fails. So for this first one, it's at as x approaches 3. And it's discontinuous at 3. The limit, so here we're using limit definitions of the definition of continuity. The limit from as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. So it fails for that reason of that. B, we have at point 1, or as x equals 1, we have a hole in the graph. So again, the rules of continuity are, does the function exist at 1? Does the limit exist at 1, and are they equal? And this one fails because it's discontinuous at 1. F of 1 does not exist, so it cannot be a continuous function. And the rule property that fails is that the function doesn't exist and have a value at x equals 1. All right, number C. I encourage you to pause the video and try to answer this one on your own. Okay, this one is discontinuous at x equals 0, similar to part B, but there is a point value. So this one, f of 0 does not equal the limit as x approaches 0 of f of x. So although f of 0 exists and the limit exists as x approaches 0, they do not equal the same value. And so that really pauses and stops it there. Okay, our next one then, I have G and H up. I again encourage you to pause the video and see if you can answer G and H. All right, G is continuous. It's a smooth curve from left to right with no jumps, holes, or asymptotic behavior. H has an asymptote at x equals -1. Therefore, it's discontinuous at x equals -1. The limit as x approaches 3 of f of x does not exist. So since the limit doesn't exist, the function does have a value at -1. It's landing on the asymptote, but the limit does not exist. So therefore, it is not a continuous function. It does not meet all 3 parameters of the definition of continuity. All right, here's an algebraic approach to working with this. Find the value of x where the function is discontinuous and identify the type of discontinuity. So for this one, it's a rational function, a polynomial divided by a polynomial. So the best way to determine if we have discontinuity and where is to use our skills of factoring. So we're going to factor the numerator and the denominator. It's going to be x plus 5 times x minus 2 quantities, and on the denominator, x plus 5 quantity times x minus 5, the difference of 2 squares. If you notice, the x plus 5s will cancel. That means there's a hole in the graph at x equals -5. So just remembering back to our rational functions from our past years, that characteristic is a hole at x equals -5. And so it reduces down to x minus 2 divided by x minus 5. So x minus 5 is still on the denominator. That is a vertical asymptote from our past at x equals 5. So we have a hole in the graph and we have a vertical asymptote. So therefore, f of x has removable discontinuity or point discontinuity at x equals -5. That canceled out. And we have an asymptote, or f of x has an infinite discontinuity at x equals 5. So just a little bit of review with rational functions, but applying discontinuity properties to them and vocabulary. Okay, example 3 gets us into piecewise functions. Determine whether the function is continuous at the value where the rule for the function changes. So that's kind of an interesting phrase. What does it mean by the rule for which the function changes? And that is going to actually be right here at x, as x is less than or equal to -1, and as x is greater than 1. That's where the functions switch. So if you think of like train tracks, it's where you're switching train tracks from one train track to the other. So that is a place where the function could have discontinuity. And so we're going to determine whether the function is continuous at that value. And we're not going to just say, yep, this is true. We are going to use the formal calculus definition above here in the top right. Is f of c defined? Does the limit as x approaches c of f of x exist? And are they equal to each other? So it's not just good enough to say, yep, we're good. You want to formally show that this f of x function is either continuous or not continuous. Okay, so for our first step, and I kind of do a checklist here, does f of -1 exist? Well, it does do that. If we take our top equation right here, we can actually evaluate f of -1, and we get 2 raised to the negative of -1, which will give us 2 to the first, or just 2. So kind of check that off. I did step 1. The function exists. The function can be evaluated at -1. The next step is to check the limits. Is the left-handed and right-handed limits equal to each other at x equals -1? So I'm going to write a little bit more formal here. I'm going to say the limit as x approaches -1 from the left of f of x equals the limit as x approaches -1 from the right of f of x. So now I'm going to substitute back in, well, what is the function f of x doing from the left and from the right? What is the equations? So the limit as x approaches -1, that is a little typo, sorry about that. It should say -1 from the left as 2 raised to the opposite of x. And the limit as x approaches -1 from the right, get that little negative symbol in there, is x plus 3, the linear function. So from the left and from the right, and the piecewise function branches show that. Okay, so now we're going to evaluate the limits from the left side and right side. So we can do direct substitution, and as long as we don't take on the indeterminate form or a number divided by 0, we're in good shape. So when I evaluate the left-sided limit, I'm going to get 2 raised to the negative of -1, which is 2. And when I evaluate the right-sided limit, I get -1 plus 3, which is 2. So the limit has the same value from the left side and right side, and the function exists at -1. The question is, in part 3 up here, are they equal? Okay, right there. And the answer is yes, they're going to be equal. The limit as x approaches -1 of f of x equals f of -1. So that's a very formal way of writing this out. It shows that you understand all 3 parts of the the continuity definition, and you're very supportive of your work. It is not just about saying, yes, continuous at x equals -1. You have to support your work with the definition. All right, example 4, and there's lots of different options for this one. It's a sketch a graph of a function that has the following values or properties. Has a value for f of 2, a limit as x approaches 2, but f is not continuous at x equals 2. So I encourage you to pause the video and try to sketch this graph on your own. All right, so let's start with kind of setting up an xy axis, and we want to say that the limit, the function value exists at 2, so our value is 2 that we're looking at. F exists at 2, so I'm going to just put a closed circle, and we'll see if we're going to connect it. The limit as x approaches, a limit as x approaches 2 also exists, but F is not continuous. So the only time, or one of the only times that a limit will exist, but the function doesn't exist there, is at a point discontinuity. So you could do something, something like this. Oop, I don't know why that disappeared. You could do something of this nature. It could be, curved down. It could be smooth continuous, but the graph will have a hole at x equals 2. So the limit will exist from the left hand and right side at some value, y value, output value here. Let's say it's just 1, but the function has a different output at 2. So the limit, the function is not continuous at x equals 2, but the limit exists and there is a function value. And there are many other images that you could use besides this graph. All right, question number 5. Find the value of k which makes the function continuous at the place where the function rule change. Again, the rule change is where the x is greater than or equal to 1 or x is less than 1. So it's where you change branches of the piecewise function. So here we actually have to find the value k. So if we know that the continuity properties are that the function has to exist at the rule change of 1, and the left-sided and right-sided limits have to be equal to each other, and then the function and the limit have to be approaching the same value. So we have to make that all happen in order to find k and make this function be continuous at that rule change of x equals 1. So again, I kind of like doing a checklist. The first one is, does the function exist at 1? So f of 1 exists, and at 1 we use the top branch 3x plus 2. When we evaluate it, we get 3. So the limit has to the function at f of 1 has to equal an output of 3. Okay, so now we're going to utilize that. So this graph has to equal 3, but in order for it to be continuous, the limit must also equal that from the left side and right side. So how do we do that? Well, we're going to set it up. So this is rule 2 of the continuity definition. The limit as x approaches 1 from the left of f of x must equal the limit as x approaches 1 from the right of f of x. So what are those two branches? They're going to look something like this. The limit as x approaches 1 from the left, 2k minus x equals the limit as x approaches 1 from the right of the linear function 3x plus 2. And what we're going to do is we need to evaluate the limits, and the left-sided and right-sided limits need to be equal. So I substituted in 1 for x, and now I'm going to solve backwards for k. So 2k minus 1 equals 5. I'm going to add 1 to both sides and then divide by 2, so k should equal 3. So the function existed, and the left-handed and right-handed limits we set equal. And in order then to do that, then we know that both parameters of the continuity function exist. Therefore, the limit as x approaches 1 of f of x must equal f of 1 when k equals 3. Okay, I'm going to skip this example, and I will come back to it. It will be finished in our completed notes, and we're going to do one last piecewise function. So here's our last example. Find the value of k, which makes the function continuous at the place where the function's rule change occurs. I encourage you to pause the video and try this one on your own. Okay, first one, make sure the function exists at the rule change. It happens to be 1 again, similar to our example 5. So when I substitute in 1, I get negative 11 out. Okay, our next step then is to force the left-sided and right-sided limits to be equal as x approaches 1 from the left and right. So then what I'm going to do is I'm going to substitute back in the branches. So the limit as x approaches 1 from the left is k squared minus 12x, and the limit as x approaches 1 from the right is k times x. So here we know that we need to have the function exist at 1, so we're going to substitute in 1, but then we need to set the k's equal to each other, or excuse me, the branches equal to each other. So then I'll get k squared minus 12 times 1 equals k times 1. Be very careful that you don't substitute in 1 for the k value. That's what we're trying to solve for. But we know that the function must, we can evaluate the function at 1 and make sure that the left side and right sided limits are equal. So it's going to be a quadratic that we're going to solve. So if you move all the variables to the left side, you'll get k squared minus k minus 12. Simply factor it. And we'll get k minus quantity k minus 4 times quantity k plus 3. So the solves are going to, the zeros are going to be at k equals 4 and negative 3. So those two values, when we plug those in, will cause the limit as x approaches 1 of f of x to equal f of 1 when k equals 4 and negative 3. So we're using a much more thorough explanation of why k has to equal 4 and negative 3 that meets all three parts of the continuity definition. All right, thanks for watching.